Hello everybody, and welcome back to my SP2 channel. This is the last lecture for this chapter. Okay, so enthalpies of reactions. For sure, we have introduction. There are going to be three different types of calculations using Hess's law, the enthalpies of formation, and the bond enthalpies. And our practice is slightly different for this session. Okay, so bear with me. You're going to see that at the end of the lecture. Okay, so in terms of the introduction, the standard enthalpy change of a reaction, which goes by delta H, and this degree signs are referring to the standard condition. I'll talk about that in a moment. And if I have the Rxn, that means the reaction, right? So this would be the delta H of our reaction, which is representing the heat absorbed or possibly released during our chemical reaction when all of the reactants and products are in their standard state. Okay, so let's define the standard state. We're going to have 1 atm for the pressure, and we're going to have 25 degrees Celsius, or you can say 298 K Kelvin. Okay, so in chemistry, they call this temperature as the room temperature, which is always funny to me because my room temperature is never 25 degrees Celsius, right? But yes, that's what they call that. So anytime that you hear room temperature, they're referring to the 25 degrees Celsius. This is our standard temperature, okay? Now, this value is going to be helping us to compare the energy changes of different reactions under very, specific conditions. Okay, so there are going to be three different types of calculation for the delta H of our reaction. The first one is using the Hess's law. We're going to be looking at that first. Then I have the enthalpies of formation. And the last one is the average bond energies. Okay, so let's take a look at the first one on the next page. Okay, so starting by the Hess's law, we have to define this law first, and then we can look at the example on the next page. So according to the Hess's law, the total enthalpy change of our reaction is going to be the same regardless of the number of the steps that we have to, produce those products. And this is just because your enthalpy is in a state function, meaning that it's going to be only depending on your initial and your final states, not how you got to the products, right? Not the reaction pathway. So it seems that we are kind of playing a game, right, in chemistry, and there are going to be a bunch of rules for our game. The first one is the additivity of your enthalpy changes. So this means that if a reaction happens in multiple steps, the total enthalpy change is going to be the sum of the enthalpy changes of all of those individual steps. The second one is reversing your reaction. So if you happen to reverse a reaction, you need to change the sign of your delta H, right? And that is totally makes sense. So the reactions are going to be endothermic in one way, but they're going to be exothermic in the opposite direction. The last one is about multiplying a reaction. So if the coefficients of a reactions are going to multiply by a factor, let's say you double your reaction, you need to do the same thing with your delta H, right? This is known as a scaling of your delta H. Okay, so let's take a look at an example on the next page. So the reaction that I have for you is a combustion of methane. That means your methane, CH4, is reacting with oxygen, and we are producing carbon dioxide and water. These three reactions are given, right? I have the formation of CO2, I have the formation of liquid water, and the formation of methane. So these reactions are given. They are part of the question stem. Now the question is, calculate the delta H reaction using the Hess's law. So when I'm looking at my overall reaction, I can see that I have methane on the reactant side. So in order to bring that to my reactant side, I need to use the last reaction, right, number 3, but I have to reverse that because I need to see my methane on the reactant side. So if you reverse the reaction, you need to take the negative of the delta H, right? So that should be a positive value here. Okay, so that's for the first step. The second step is I'm going to write my first reaction as it is because I need to have carbon on the reactant side and I need to have CO2 on the product side. So if you write it, you just need to write your delta H as it is. The third one is using the second reaction, right? Reaction number 2, but I need to double that. So think about it for a moment. Why do I need to double this reaction? Yes, absolutely, because I need to have 2 moles of water on my product side, right? If you double that, you need to double your delta H as well, okay? Now, let's sum them all up. Okay, so if I have anything on the reactant side of one reaction and the product side of the other reaction, you can call that kind of intermediate, you can cancel them out. So I can cancel my carbons here. I can also cancel my hydrogens, right? You can write the rest of the reactants and products, and that goes by methane reacting with your oxygen gas. We're producing CO2 and water, right? And just need to sum all of these delta H's. So the delta H of our reaction is negative 890.3 kJ per mole. That's an exothermic reaction, which is making sense, right? Because combustion reaction must be exothermic. Okay, cool, cool. Looking at the next one. Okay, so here's the second one, which is the enthalpies of formation. So let's define this enthalpy of formation first, and then we can look at the ultimate, equation, and then I have a practice for you. Okay, so by definition, the enthalpy of formation is the enthalpy change when one mole of a compound is formed from its elements, and it must be at their standard states. Great news for you guys. If you have the, any of your elements at the standard state, the standard enthalpy for them is going to be 0. So for example, if you have oxygen gas, right, nitrogen gas, if you have bromine, if you have carbon in the form of graphite, right, they're going to be only 0. That means our calculation would be a lot easier, right? Okay, so keep that in mind. The enthalpy of formation for a compound could be positive or could be negative, depending on whether the energy is going to be absorbed or released during the formation of that compound, right? Now, all you need to do is you need to look at the table, right, that is giving you all the enthalpies of formations, and I'm going to show you an example in just a moment. Now, here is your ultimate equation. You will look at all of your products, right? You would sum them all, do the same thing for the reactants, and then take the difference. Okay, that's how we can calculate the delta H of reaction using the enthalpy of formation. So here's the table. The table is going to be really, really big. I just have a portion of that for you, right? And you don't need to be worried about that because this would be given to you, right? I just want to make sure that you're aware that we have like positive, negative, large, small values for these, enthalpies of formation, right? Whatever is the case, it would be given to you. Also, be careful with the state. For example, if you look at what I have here for water in the liquid form, and the water vapor, they have different amount of energies, right? So be careful when you are, selecting your values. You also need to look at their phases, their states. Okay, excellent. So looking at the next page, that is where we have a practice. Okay, so this is the exact same reaction as we did for the Hess's law. Okay, now we're going to do again our calculation, right? But using the enthalpies of formation. Okay, so all of these values are given. As you can see, you have the delta H formation for your methane, for CO2, as well as liquid water. Okay, so here's my equation. I need to look at my delta H formation for all of my products, sum them up, and then do the same thing for your reactants, and then take the difference, okay? To make it a little bit easier for you, I did a color coding, okay? So all of my reactants are in blue color, and the products are in the purple color, okay? So take a look at your product side. You're taking these values from the table that is given to you, right? And make sure that you look at how many moles of each we have. We have to be careful. So for example, here we have 2 moles of water, so I need to double that. Do the same thing for the product, and then you take the difference, and that is going to give us negative 890.3 kJ per mole, right? Okay, cool, cool. So looking at the last one. Okay, so here's the last one, which is using the bond enthalpies. Okay, so by definition, the bond enthalpy, or maybe bond energy, you can say either of them, is presenting the amount of energy required to break 1 mole of a particular bond in the gas phase. Okay, and this is typically measured in a form of kJ per mole, and it's representing the strength of a chemical bond. So if I have a stronger bond, I'm expecting to get even more energy, right, that is required to break that bond. Okay, so we have to be careful with the positive negative signs here. If you try to break a bond, that means we need to invest energy, we need to add energy to break that, which is going to be an endothermic process, so positive delta H. But if the bond is going to be formed, right, then we are expecting to get a releasing of the energy, which is going to be exothermic process, negative delta H. Okay. Now, here is our ultimate equation. We're going to have the delta H of our reaction. You're looking at all the bonds that are broken on the reactant side, all the bonds that are being formed on the product side, and then you take the difference of these two. Okay? Cool, cool. So looking at this table, this is again, it's going to be a pretty, large table. This is just a portion of that. But because we have all of these energies that are required energies, so they're going to be always positive value, right? We're not going to have a negative value for the bond enthalpies. Also, be careful that what I have here is the average bond, which means that they were looking at all the compounds that they had CH bonds, and they were taking the average of all of those energies, right? Which is given on this table. Okay, so we're going to look at the practice, okay? And again, we're looking at the same reaction. That's a combustion of methane. These energies are given, okay? So looking at your reactant side, where we have all the bonds that are broken, I have 4 by 4, 112, which is going to be the 4 bonds that I have on the methane molecule. And then I have 2 by 498, which is the amount of energy that I need to spend to break the OO bonds for the 2 moles of oxygen gas. On the product side, I have 2 by 799, which is the 2 bonds for the CO in your CO2. And we also have 4 of the OH bonds for the 2 molecules of water. So each molecule has 2 bonds, and because I have 2 of them, it's going to be 4 by 463, right? Okay, so that is going to give us negative 806 kJ per mole. Okay, cool, cool. So let's take a look at all of these 3 calculations that we have done together. Okay, when we were using the Hess's law, we got this much kJ per mole. When we were using the enthalpy of formation, right, we got the same answer, right? But when we were using the average bond energies, the value was slightly different. So I'm going to say that I have a little bit approximation, right, for the delta H calculation using the average bond energies. The other two, 1 and 2, are going to be always the same, but we're going to get a slightly different value using the average bond energies, okay? So I'll talk about what are the possible reasons for having this kind of discrepancy in our calculation, okay, in our future lectures. But I want to ask you guys, so here's the question for you. Think about it. What could be the reason that the energy that we got using the average bond energies was different than the other two? Okay, you can comment that below. Cool, cool. A very big thank you to all of you for watching this video. If you like it as much as I like it, you can give me a thumbs up, right? So this is going to be our last lecture for this chapter. I'm going to see you guys soon, starting our new chapter. Take care of yourself, and bye-bye for now.